Hello, once again, I'm Dr. Sixbert Maurice from the Department of Crop Science and Production, and this is our second lesson in the series of precision agriculture or Introduction to Digital Agriculture. And today we are going to be looking at the principles or the basics of geographical information system. Very good. So, what is a geographical information system? Here we are saying that GIS, in short, is a term that is used to describe the software that has the capacity to conduct analysis and create maps using geospatial information. So we look at the components of a GIS and we say that we have the first component is what we refer to as data layers. So these data layers have two components. The first one is the geometry and the second one is the attribute table. A data layer is representation of a real-world object. Now, all real-world objects can be mapped as features on a map, and that is the geometry. For example, a polygon feature representing field boundary. Now, this field boundary is what we refer to as a real-world object. So the data layers are represented as the points, the lines, or polygons. Now, these three are what we refer to as the geometry. We look at the attribute table, the other component, because we have looked already at the geometry, and now we are going to look at the attribute table. Now we say that the attribute table is an organized matrix within the data layer for storing the data. So it has rows, which in other words we call them records. Now these rows or records contain information for specific feature. And it has columns, which we refer to as fields, in other words, for storing attributes or the characteristics of each record. So here I'm giving an example of how the attribute table looks like. So we have the records, and then we have the fields, as I've just said. And this is the list of features. This is the list of features, and here we are seeing that we have several polygons. So we have maybe 7 polygons, and each polygon represents the boundary or represents a specific area, and this is within the Morogoro municipality. And I'm assuming that these polygons represent the words, some of the words within the Morogoro municipality. Now, how does GIS work? I mean, what is the importance of this GIS or Geographical Information System? We have several functions of geographic information systems, but I'm not going to exhaust all of these functions, but I'm just going to give you few but most important functions. So we have one which says that we could display data layers, and these layers can be used to make a map. Okay. But the second one is the storage. So the first one was display, and the other one is storage of data within these attribute tables. And the other function is retrieval of data, that once we have stored our data, we need some ways to retrieve, to get back those data, the attributes in terms of columns, and for each feature in terms of records. And the GIS can be used to access all of this data, and this is what we call querying. So the whole data set the whole database can be queried so that we retrieve the appropriate information that we want. The other function is to manipulate data for accuracy and usability. Now, there could be some errors in our data. So how do we correct those errors? It means we need to go into the database and make some, into the tables and make some corrections. And we could do this when we have a GIS system in our machines. The other function is to analyze the data so that we can get a glimpse of what this data is all about. So we can summarize, we can combine, we can compare, and we can establish the relationship between layers of the data. Last but not least is that we can make presentation of the data into multiple maps, charts, etc. for interpretation of the data. So we have looked at few functions of GIS. Now these are the things which GIS can do. Okay, so we say that there are three types of data format under vectors. So we have a vertex. This is a vertex, and we have a segment, a line segment, meaning that for points, these points do have just vertices, but the lines must have a vertex, but together with a line segment like this. So as I said earlier on, we said that points have vertices but no segments, whereas lines must have at least two vertices, meaning that you have one vertex here, but then you need to have another vertex here, but then you need to have a line segment in between which connects these two vertices. As for polygons, so we say that at least three vertices should be there and segments. Now, an additional property of polygons is that these two, the two vertices, the last and first, should have the same value. We are going to look at this in more details shortly afterward. The rasters. Now we have done with the vectors, vector data layer. Now we are going to look at the rasters. So we say that rasters store data in a grid or a series of rows and columns that form grid cells. And these grid cells are referred to as pixels. Now each pixel represents a specific area in a real world, and each pixel has a location data but has one attribute table value. So locational and attribute values are typically measured at the centroid or the middle of the grid cells. So this figure here is a simplified representation of how a raster looks like. We said that you have a series of rows like this, but you also have a series of columns like this. Okay. Now, the intersections of these rows and columns form what we refer to as a pixel. And you can see here at the middle here is, highlighted green. So that is the pixel. Now, this pixel at the centroid of the pixel, at the center of the pixel, that's where you have locational and attribute value at the center or at the middle of the grid cell. There are two types of raster data formats. One we call raster grids, and we say that this has one value pixel, which is an attribute value of that pixel. And these raster grids are created using GIS tools. We're going to see how. Okay. So this is in the small picture, you can see there are features, and these features, the real world features, are represented in various colors. So you have the blue here, which looks like a river, but then you have the brown, and then you have the green. Now, if this green section is exploded, you'll see individual pixels. So you have the cells here. Okay. So another type of raster is what we call raster image, and we say that the value for a pixel is a color value, as in a georeferenced digital photograph. So raster images are created using cameras or sensors to capture light reflectors. So in this picture, you can see it is a very large picture in which we are showing vegetation. There is a vegetation here, and this vegetation is represented in terms of color value, in terms of pixels, which contains color values. And these pixels, if you try to blow it up, you'll see there are pixels, and these pixels have location value and attribute values for each cell. We'll go ahead and look at the scale. Now, because we are representing real world features in a map or in a piece of paper, then we need to know the scaling of that map or picture in a paper, how much it represents in the real world terms. So we say that the scale is a ratio of a map distance to the real world distance. For example, a scale of 1 to 2,500 means that 1 centimeter on the map represents 2,500 centimeters on the real world. This is an example of how we present scales in GIS related aspects. So we use the scale bar. So this is the scale bar, we call scale bar. And here we can see that this scale bar shows how many kilometers on the real world are represented by 1 centimeter on the map. Okay, so here we are saying that 1 centimeter represents 1 kilometer on the real world. We move forward and look at projections or coordinate reference systems. Projections and coordinate reference systems. Maybe we try to conceptualize something. Think about how difficult it is to peel an orange in one piece and try to flatten that peel. Okay, so you will see I've given this example. This is the globe. In its spherical shape, you have this shell here. But if you've tried to flatten it, you can see how much challenging it is if you wanted to have a perfect flat surface like that. So projection is a process of transforming a spherical Earth surface into a flat surface map. That is the real meaning of projection. Yeah, because when we make presentations, we normally present our maps or our raster images on a flat piece of paper or a computer screen. Okay, now we need to find some way to project the spherical object, because the Earth is mostly spherical, so that it can fit onto our flat surface presentation. So the role of projection is to remove errors that are associated with location, the size, and orientation of map objects rather. Okay. So the coordinate reference system, the CRS, defines how a two-dimensional projected map in GIS is related to a real location on the Earth, as I've said. Now, the choice of the coordinate reference system to choose depends on two things, or three things rather. One is the regional extent of the area that you want to work in, whether this area is in the north or southern pole, or it is near the equator. Okay. But also the analysis that you want to do and the availability of data. So essentially, there are two types of coordinate systems. The first one is what we call a geographic coordinate system. And this one uses degrees of latitude and longitude. For example, the most famous World Geodetic System, and you will find in many presentations, it is known as WGS 84. So here's our globe. Okay, so every location on the Earth's surface is given in terms of the degree of latitude. It means the angle that is subtended by a vertical, the angle that is subtended to the y axis, but also the longitude. Okay. The other thing is what we call projected coordinate reference system. This is another coordinate reference system, but it is called projected. Okay. And here we are saying that this is a two-dimensional coordinate reference system that is defined by two axes. Instead of using the degrees, the angle degrees, here we use what we call axes, x and y. And the most popular coordinate reference system under this category is the UTM, the Universal Transverse Mercator. Now, to avoid distortions that are accompanied with flattening a spherical object, the world is divided into 60 equal zones, and each zone has 3 degrees each. Okay, so here we are saying that the coordinates are presented as northings, okay, and eastings, and the coordinates are measured in meters. Okay, so the UTM measures the coordinates in meters, whereas the WGS 84 uses the degrees. Now, how does GIS work in precision ag? Now, here we are saying that precision agriculture requires GIS to analyze and display georeferenced data. So a GPS would be needed to collect the data, and this collected data needs to be converted into GIS layers with appropriate coordinate reference system, whether it is a UTM or a WGS 84 system. For example, vector polygon layers, where you will be showing the soil types, the field boundaries, etc., etc. Or vector points, where we'll be showing the points where we obtained soil samples, the points where we spotted some pests or some diseases. But also the raster images, like the field images, or the raster grid, for example, the field normalized difference vegetation index, or NDVI. GIS is also associated with a substantial amount of data analysis. And we say that data analysis is needed to summarize or organize and convert data to information, because data cannot be easily interpreted, but once it is converted into information, that people get to know what it is, what the data represents. So the key considerations in data analysis include things like thematic resolutions. It means how many categories of map features that can be represented, for example. The spatial resolution, like how many centimeters on the map represents how many kilometers in the real world situation. Associated with the GIS data analysis is another important aspect, and this one is what we call GIS spatial query. So we say that query is a data retrieval tool, and it allows the user to select a feature or a group of features based on some criteria. For example, if one wanted to know all the fields whose soil pH is less than 6, so this pH less than 6 is a criteria. So we'll set this criteria and query the GIS database to show us all the fields whose pH is less than 6. Associated with GIS data analysis is the statistical summaries. We are saying that the data that is within the GIS can be analyzed to get us the summaries, to get us the information. Now, such statistics as the mean, the sum, the standard dev, etc., can be summarized from the data set. The entire GIS data set, or part of the data set from the query. Like what we've just said, if you wanted to get only the fields whose pH is less than 6, for example, so we'll get the areas, the mean areas of those fields, for example, the sum of those fields, the standard deviation, and so forth and so forth. Another aspect associated with the data in GIS system, in the GIS rather, is data interpolation, and the main purpose of this activity is to convert vector point data to raster grids. So interpolation uses mathematical functions to calculate an estimated value for an unknown point using 2 or more known points. I'll give you an example. Like here we have our map, for example, but we know this point X, and we know another point, let's say W, okay? But we don't know what is here, and we don't know what is here because we didn't have time or resources to collect data over these unknown points. Now, interpolation would use this point and this point to estimate what are likely to be in these places where we didn't have time or resources to collect data about. So interpolation can be used to create nutrient maps, for example, from 2 or more points. Reclassification. This is another aspect which is very much associated with data analysis in GIS, and its meaning is to convert data into discrete categories. For example, classifying elevation of the farm. Okay, let's say you have your farm looking like this. Okay, but here you'll see you have so many variation within your field, like this. But if you wanted to leave it as it is, you'll see you have so many categories here. But for ease of interpretation, we'd want to have maybe 3 categories. Maybe we'll have valley bottoms, and then we'll have crests like this, and then we'll have a sloping area like this. So here we'll have 3 categories, for example. So we'll have this being category number 1, the valley bottom being category number 2, and this sloping place being category number 3. So simply, it is easy to interpret less categories than if you had so many categories. So that is the real essence of making reclassification. So this is the continuation of the example that if you wanted to do reclassification, we'll just take the mean and maximum elevation, for example, and create 4 categories of elevation ranges. Now, for each of these categories, because we have 4, we'll just give them an integer and say we have 4 classes of elevation in our fields. Okay, and thereafter we can create a class map which will show all of the 4 categories that we have in our farm.